Welcome and hello. This is a video lesson in WRIMS, and in this lesson, we're going to be talking about the objective function statement. On the screen, I'm going to put up the model schematic for this lesson, where what we have is two reservoirs in parallel. They both have channels that drain down to this node 3, so channel 1-3 and channel 2-3 flow from reservoirs 1 and 2 respectively down to this node 3. Downstream of node 3, channel C30 does have a downstream flow requirement. I'm going to open up DSS View and check out what that flow requirement is. This is a table. We're going to be running a 3-year simulation on a 1-month time step. And what I've done is just ramped up the downstream flow requirement from 1 up to 36 or 37, increasing 1 CFS per month. So there's the plot of that. And then that demand needs to be met by the reservoir storage, which is in reservoir 1 or reservoir 2 or both. All right, I'm going to bring up the objective function. Objectives.russell is where I'm keeping my objective function. So this is my specific objective function. This can be described in the Russell Plus reference manual, which is right here. It's on page 19 of this version, and it talks about how this is the standard format. We have the keyword objective, then the name of the objective. And I've always needed to put in an equal sign right here before the opening bracket. And then in order, just go ahead and list out the name of the variable and then the value expression. Oops. Okay, this value expression here would be the value itself. So typically just a number, or it could be some sort of expression that represents a number, and that would be the weight. So let me go back to my example right here. So what I have is I say the flow through channel C1 has a coefficient of 10, and then the flow through channel 2-3 has a coefficient of 5. So WRIMS is trying to maximize this objective function, and I can basically rewrite this out to a more readable format if I just do something like this right here. So the objective function value equals 10 times through channel C13 and plus 5 times the channel flow through channel C23. So that's all that this is trying to convey here, is to maximize this left-hand side by modifying these two parameters. If there aren't any other constraints, it makes sense to maximize this value right here. Now, the only constraints I have is non-negativity constraints on these channels. So if I click on channels, here is where I'm defining the channels. This STD basically means they cannot be negative. The minimum value for the flow through these channels is 0. I do have a constraints file, and that just is the continuity of the reservoirs and then the continuity at node 3. There's no maximum flow restriction on the flow through channels 1-3 or 2-3. So here's the diagram once again, and then back to the objective function. Okay. So if we ran this, we're probably going to get the entire flow through channel C13 because it has a higher coefficient, 10. Let's go ahead and see if that works. So I'm going to remove my comment here, save everything, and then go to WRIMS. Here's the launch file. I'm going to right click, run as, and then just run it. Okay. Next, I'm going to go over to my DSS view, open up the decision variable file, db.dss, and then view, refresh catalog. All right, so here is my 2 channel flows. Here are the numbers, and sure enough, all of the downstream flow requirement is met by releasing water through that channel C13. The flow through channel C23 remains 0. And if we look at the plot by clicking on the plot button, blue is the flow through channel C13. This is a monthly time step over the course of 3 years. And then the red line here is 0. That's the flow through channel C23. We can also look at the reservoir storage. So if I open up the plot, this first plot here is the plot we just saw with the flow through the 2 channels. And then the bottom plot here is the total storage in reservoir 1, which is green and it's draining, and then reservoir 2, which is red, and that remains constant because it's not draining. There's no inflow in this model, just release from the reservoirs. Just trying to keep it simple. Okay, so with that in mind, what would happen if we go back to our objective function statement and increase the coefficient here, or what's sometimes called the weight of this variable, which is the flow through channel C23? Well, as you may imagine, the opposite situation is going to happen. All the flow is going to be now through channel C23. So we can go back to WRIMS and then right click, run as, go ahead and run that. Back to DSS view, refresh catalog, And then I'll just highlight all 4 of these paths here and click on the plot. Okay. Now right here, 0, that's the flow through channel C13, and then here in red at the top is the flow through channel C23. Now you may be wondering, how do we get those 2 different flows to be the same? You may be tempted to just change the weights to equal weights, and that is not advisable. At least I don't advise that. But what you could do is create a constraint to penalize any deviation between these 2 variables here, a soft constraint. So I'll come over to my constraints file. Okay, I just pasted in this constraint right here. It's a soft constraint, which basically means if there's a violation between any deviation between the flow in these 2 channels, it's penalized by 20. I just arbitrarily put 20. That's larger than 5 and 10 and even 15. So let's go ahead and save everything and then go back to RIMS and then right click and run. I'm not going to show every time I run because that's redundant. Same thing with DSS. I'm not going to show every time I go view, catalog, and refresh. Okay, I'm going to highlight these 4 paths once again and click on plot. So now we have an equal release from channel 1.3 and 2.3, and then down below, and since both reservoirs have the same starting volume, then you see that their volume depletes at the same rate. Okay, let's go back to our objective function. I'm going to remove this constraint right here, save that, and then here is our objective function. Rather than just a constant value right here, let's try something else. I'm just going to demonstrate a few different things we can do with this objective function statement. Here we have the flow rate through that downstream constraint, C30. That's going to be serving as the weight for the flow through channel C1. And then the weight for channel C23 is going to be 40 minus that value. So remember, this downstream flow value starts at 1 and it ramps up 1 CFS per month. So 1 to 36, which means this value is going to increase from 1 to 36, and then this value is going to decrease from 40 down to 4, which means for the first part, the first 20 months of the simulation, we're going to be releasing water here through channel C23. And then after that, it's going to be from channel C13. Okay, so I'm going to go ahead and save that and see what happens. I ran the model in RIMS. Let's go and view, refresh, and then highlight those fields and click on plot. Okay, just as expected, what we have is no flow through channel C13 for the first 20 days, or 20 months. I'm sorry, 20 months. And then the opposite is true. We have only flow through C23 for the first 20 months. Down below here is the volume of reservoir storage over the course of those 3 years. So you can see how that responds for reservoirs 1 and 2. Let's go back to our objective function right here. And then here is another example. What we're doing here, this is sort of another way to keep the volume of the reservoirs equal, but it doesn't really work that well. What it's going to do here is we're referencing 100 minus the storage in the other reservoir at the previous month. So 1.3 referencing reservoir 2, and then 2.3 referencing reservoir 1 from the previous month. I'm going to go ahead and save that and run it. Okay, so I ran the model. Go up to the view, refresh. And then let's take a look at those results. So what's happening here is every other month, the reservoirs are trading off which reservoir is going to release the water that month. So in blue here, this is the release from reservoir 1. This is the release from reservoir 2 in red in the top plot. And then in the bottom plot, green and red are the storage in reservoirs 1 and 2 respectively. If we wanted to do the same thing, but for instance, maintain a 10,000 acre feet difference between the storage and the reservoirs, what we do is just go back here, maybe change 100 to 90, and then save. Okay, back to DSS view, and then refresh, and then select the paths once again. Here what we have is we're only releasing water from reservoir 1 for like the first year and a half of the simulation. And at that point, we have a 10,000 acre foot difference between the volume in the reservoir. And that's when we start trading off on the releases between the 2 reservoirs. Reservoir 2 is 10,000 feet, approximately 10,000 acre feet above reservoir 1. Okay, so you got the idea of how the objective function works. Next, what I want to do is introduce construct in the Russell Plus programming language called intrinsic definitions. And this may come up in future lessons and exercises as well. I may have talked about it already. but the terms days in, month, and water year can be used as reserved variables which resolve to an actual value based on the simulation itself. So days in represents the number of days in the current month. So that'll return 31 for January. This example here just creates a state variable XYZ, and then value days in will be 31. Month will resolve to the number of the month of that simulation. So 1 is in October, 2 is November, 3 is December. I should say December is 3, January is 4, February is 5, and so on. That's just the way the California water year works. So that's how it's programmed into Russell Plus. After that, we have a water year. So that would be the 4-digit year. So October 1921 will resolve to 1922, for instance, but September 1921 will resolve to 1921. Okay, so just keep that in mind. The water year begins in October. And then the last two here, this capital MMM resolve to the lowercase 3-letter abbreviation for the month. Previous will resolve to the time step position of the specified previous month relative to the current month. So, for instance, if it's currently December and you type in previous October, it's going to return a -2. All right, so let's go ahead and kind of mix this in with our objective function statements just to do something fun here. Let's start with days in. So days in, remember that returns the number of days in a month. January is 31, February is 28, or I suppose 29, March is 31, and so on. Back to our objective function, I'm going to paste this in. So we're using C13 and C23 again. I'm going to set the value of flow through C13 at 29.8 and then days in as the weight or objective function coefficient for C23. Now what's going to happen here is in February, days in is going to be 28 or 29. So only in February are we going to have flow through C13. All the other months will be through channel C23. Let's go ahead and save it and run it. Okay, I ran it and then I refreshed the catalog. Here is what's happening. Here we go. Just in February, we have the release for Reservoir 1 to satisfy that downstream flow. And then all the other months are satisfied via release from Reservoir 2. And then down below, you see the corresponding decrease in storage in Reservoir 1 and Reservoir 2. All right. Now, if you wanted to get a little bit more tricky with this, you'd probably use conditional statements and logic, which is not supported in objective function statements, at least not according to the Russell Plus user's manual. That sort of flexibility can be created in your constraints. So we'll deal with that at a later lesson. Now, instead of 29.5, if I just change it to 30.5, then approximately half the time, about half the months, have a number of days more than 30.5, and about half have less than 30.5. So let's go ahead and see what happens there. I'm going to run the model again, and then let me refresh the catalog. Let's take a look at that plot. Okay, so here we go. In blue is the release from Reservoir 1, and then red is the release from Reservoir 2. There are a few more months with 31 days in them than less than 31 days, so we start to see a deviation in the storage in this bottom plot. Back to the objective function, let's try another one. Another one of these intrinsic definitions is month. So remember, month just counts from 1 up to 12. 1 is October, 2 is for November. This basically means, like, if I hit a 6 right here, then for the first 6 months of the water year, we're going to be releasing from Reservoir 2 and Channel 2-3. And then, well, once it's 6, there's going to be some sort of arbitrary tie-breaking procedure. It could be a combination, but basically, once the month is greater than 6, we're going to have flow through Channel 1-3, which is release from Reservoir 1. So let me run that. Okay, I've refreshed my decision variables, and let's take a look at that plot. As expected, we have release from Reservoir 1 about half the year, release from Reservoir 2 the other half the year, and then the storage in those reservoirs is shown down below in green and red. Okay, I think you get the idea. I'm going to throw one more in here just for fun. This is days in and then month times 4. So remember, days in is going to be 28, 30, 31 for the most part. And then the month, this is going to be the number from 1 to 12. I'm multiplying it by 4 just so that this value will sometimes be larger than this value. Let's go ahead and check that out. I ran the model successfully. Let's refresh the catalog and take a look at these results in the plot form. Looks kind of similar to last time. About half of the months are going to be satisfied with release from reservoir 1 and reservoir 2. And then this is the storage in reservoir 1 and storage in reservoir 2. All right, I hope that was helpful. This is the end of the lesson where we talked about the objective function statement and also talked about intrinsic definitions using a simple model here in WRIMS.